This is a little extra episode of the Higgs boson discovery explained. Let's call it episode 3.5. And in this short video, I'll answer some of the questions that you had in the comments, and I'll expand on some of the points made in the other videos. So if you haven't seen the first 3 episodes, it probably makes sense to watch them first. You can find the link in the description below. That said, let's go. I'll start with a question that came up quite a few times, and that kind of picks up where the series left off. So how do we know that we found the Higgs boson? Well, we have to study the properties of the particle that we discovered and check if they match what's expected for the Higgs. So the first step is finding something. If we see a peak in the invariant mass spectrum of 2 photons, we already learned that there's a particle there, and we learn the mass of this particle, and we learned that it decays into 2 photons. And in the first approximation, it would seem that that's it. But actually, using certain rules that govern the particle world, we can extract some more information from just this one peak. For example, we can learn the electrical charge of this particle. Because if the particle decays into 2 photons, and a photon has 0 electrical charge, this particle also has to have 0 electrical charge, otherwise this decay would break charge conservation. The next thing is a property called spin. A particle can either have integer spin, making it a boson, or half-integer spin, making it a fermion. And in the standard model of particle physics, we have elementary fermions, the quarks and the leptons that make up all matter, and they have spin 1/2. And we have elementary bosons that are responsible for the interactions, and they have a spin of 1. So the mathematics of spin is such that if a particle decays into 2 bosons, it also has to be a boson. But actually there's an extra law saying that if a particle decays into 2 photons, 2 massless bosons, its spin cannot be 1. So in practice, this leaves us with either 0 or 2. Less than a year after the discovery, using the extra data collected and a complex analysis of the angular correlations between the directions of the decay products, we were able to essentially rule out spin 2, establishing this new particle as a particle with no spin, what we call a scalar boson, which is what the Higgs is supposed to be, but it's actually quite a profound result in itself, because this is the first elementary particle with no spin that we have seen. We know other particles that have no spin, for example the pi mesons, but a meson is not elementary, it's a quark-antiquark pair. But the real test of whether this new particle is the Higgs boson or not is checking how strongly it interacts with other particles. Because for the Higgs boson there's a very specific pattern here. The Higgs interaction strength depends on mass. The higher the mass, the stronger the interaction. So how do we test this experimentally? Well, let's look at the life of the Higgs boson. It has a beginning and an end. At the beginning, the Higgs is produced from some particles, and then at the end, it decays into some particles. And in both cases, the probabilities of these processes happening are influenced by the interaction strength. But these are things that we can experimentally measure. We can look at the probabilities of different Higgs decays, measure them, compare them with predictions from theory, and check if everything agrees. And so far, within the precision that we have and for the decays that we are able to measure, everything agrees very well. How many Higgs boson decays to 2 photons does the diphoton discovery plot show? Well, let's start with this. How many photon pairs does it show in total? So the plot covers a range of masses between 100 and 160 GeV, and it has 60 points, which means that each point is telling us how many photon pairs we found in a range that's 1 GeV wide. For example, the first point in the top left tells us that we have about 4,500 photon pairs with invariant mass between 100 and 101 GeV. So you can add all of these up and you'll get the total number, which is of the order of 150,000–160,000 photon pairs. So how many of these are Higgs boson decays? Well, you can read it of this plot. At first you might be tempted to say, okay, so that's the height of the peak, so 2,700. But that's not the height of the peak. Because if there was no Higgs boson, you would still have about 2,500 photon pairs at that mass. So the height of the peak is the difference between that and what we're seeing, so about 200. But 200 is also not the right answer. Because the peak is not just this one point, but also the ones next to it. And that's because we calculate the invariant mass from measured energies and directions of photons, and these measurements have some uncertainty. and this uncertainty washes out, spreads out the results a little bit. So the total number after adding all of this together is of the order of 500. So this plot contains 150,000 photon pairs, and only 500 of these are Higgs boson decays. But we can see that they're there because of this peak that they're forming. A few of the questions that came in revolved around the Higgs mechanism itself, and things like, if the lifetime of the Higgs boson is so short, how can it give mass? Well, I have a short answer and a medium answer. So the short answer is where to find the long answer. We have several videos on the topic on our channel already, so we'll put in the video description down below links to these. Now, the medium answer, I'll try to, well, maybe not explain it, but I'll try to very briefly clear up a few things. So, very quickly, how does the Higgs boson give mass if it's so short-lived? Well, it doesn't. That's a misconception that somehow appeared, but it's not the Higgs boson that gives mass, it's the Higgs field. The Higgs field is something that fills up all the universe, it's literally everywhere. And indeed, particles, as they move through it, they gain mass by interacting with this field. So what's the Higgs boson then? Well, the Higgs boson is a little excitation like a wave in the Higgs field. And we needed to prove that the field exists, because we have no sensors capable of probing, of detecting the Higgs field directly. But if we're able to make a wave, well, if there's a wave, it means that something must be waving. You cannot have a wave all by itself. So finding the Higgs boson proves that the Higgs field exists. The Higgs boson doesn't give mass, but it's a way of detecting something that does. Another thing that came up a lot in the questions is, how do accelerators work and where do the protons come from? Well, the protons come from a bottle of hydrogen, because the hydrogen atom is just a proton and an electron. If you take the electron away, you're left with a proton. But we actually talked about this in detail in a recent live stream from the LINAC 4 accelerator. We have another live stream planned for later this year from the Large Hadron Collider, and possibly some more videos on the topic. So we'll keep updating the video description with links to whatever is available. Meanwhile, you can of course subscribe to this YouTube channel to be notified straight away, and I'll see you soon.